If we start on the bottom of the OSI model, we'll find our first layer, the physical layer. Now, this is where bits are transmitted across the network and includes all the physical and electrical characteristics of this network. So this is going to tell us whether we're using an Ethernet network, whether we're using fiber or copper cables, whether we're using Cat5 or Cat6, and even if we're using radio frequency in the case of Wi-Fi. Regardless of which method we're using to send our data across this first layer, it's always going to occur as bits, and these are binary bits. These are going to be a series of ones and zeros. Now, each media has a different way of representing these bits, these series of ones and zeros, because these series of ones and zeros are the basic building blocks of all of our data. For example, if I'm using a copper wire, such as in a Cat5 or a Cat6 network, you may see that there's 0 voltage on the wire when you have a 0 bit. And then if you want to represent a 1, you might use +5 or -5 volts on that copper wire. Now, when we switch between these two modes, this tells us whether we should read a 1 or a 0 on the network. And this is called transition modulation. Now, for the exam, you don't need to understand the specifics of transition modulation, but you should understand this basic concept that on this wire, we're going to have one level that represents 1 and another level that represents 0. Let me give you another example. This time, let's pretend we're using a fiber optic cable. Now, with fiber optic cables, we're going to use light instead of voltages. Now, it's similar to the way we did voltages, but instead, when we want to represent a 1, we turn the light on. If we want to represent a 0, we turn the light off. Now we can just read the state of the light. Is it on? That's a 1. Is it off? That's a 0. And when there's a transition between, that tells us between these two modes whether we should be reading this as a 1 or a 0. Now, as we start understanding that, we then have to look at the cables themselves, because this is also part of our physical layer. If we're using something like a Cat5 or a Cat6 cable, we may have a certain connector on the end, called an RJ45, which allows us to plug that cable into the back of a computer or into a switch. Now, the way that connector is wired is based on a certain standard. We use two standards inside our network, TIA-EIA 568A and TIA-EIA 568B. Now, we'll talk about these and which way these pins actually are set up inside this connector in a future lesson. This is going to be important because as we start talking about these, this is going to tell us whether or not we're using crossover cables or straight through cables. If we use a crossover cable, we're actually going to flip the transmission and receive bits on the end of the cable. So one end will be the A standard and one end will be the B standard. But if we're using a straight through cable or a patch cable, we're going to have the B standard on both sides. Now again, it's important to understand these wiring standards, so we're going to spend some time on them in a future lesson, because on the exam, you may be asked to wire up an Ethernet jack. Maybe they're going to tell you to make a crossover cable, and you have to drag the right colors to the right pins, that kind of a thing. And so to make sure you're ready for that, we're going to cover that in a separate lesson. Now, at this point, we've talked about having our cables, we've talked about how we represent bits on those cables, and we talked about how we're going to set up the connectors of those cables. But there's another thing we have to think about at the physical layer, and that's the topology of the network. How are we actually running these cables to physically connect the different devices together? Well, when we look at this from a layer 1 perspective, we can look at this based on the things we talked about in the last section of the course. Is it a bus? Is it a ring? Is it a star? Is it a hub and spoke? How about a full mesh, a partial mesh, or any other topology that we discussed? When it comes to figuring this out, you're going to look at how they're physically cabled, and if you drew them out, does it make a line, like a bus, a ring going in a circle, or a star pattern? And that'll tell you what physical topology you have. This again is a layer 1 issue. Another issue that we have to concern ourselves with at layer 1 is synchronizing our communications. We have to ask ourselves, how does the receiving end know if it's ready to accept ones and zeros that we're going to send it? Now, this sounds like a really easy thing to do if we're talking to each other, but with computers, this can get much more complicated. So to make sure that we understand this, we have two things that can happen. It can either be transmitted asynchronously or synchronously. Now, when I'm looking at asynchronous communication, you should be able to consider something like a voicemail. You call up your friend, they don't answer, and so you leave a message so they can listen to it later. The communication happens out of sync or out of time. You do it, and then later on, they can go back and listen to it. Now in networks, this happens via a start and stop bit. Similarly to how your friend can press play on their voicemail system to listen to their message, a network can send a start bit when it wants to start beginning the transmission, and then a stop bit to tell the other side, hey, I'm done transmitting, you've gotten everything I'm going to send. Now, if we decide to go and do communications synchronously, on the other hand, we have to be in the same place at the same time. So in our previous example, if your friend picked up the phone and you had a conversation, you could talk to them and they could talk to you. This is a synchronized conversation because you're both talking at the same time. Now, this communication happens in real time. That's what's great about synchronization. Now, as far as when we start talking about this from a network perspective, instead of using a start and a stop bit for synchronizing, we would use some sort of common time source. And so maybe we're all going to use a clock. And every time a second passes, we can transmit and receive. And that tells us that we're going to do it on the cadence of the beat. That would be something that is synchronous. Now, in addition to figuring out if it's going to be asynchronous or synchronous, you also have to figure out how you're going to utilize the bandwidth of the cable. And there's two main ways that you can do this. One is called broadband and one is called baseband. Now, broadband is going to divide our bandwidth into separate channels. If you have a TV service at your house, you're probably familiar with this because you have a single cable coming into your house, but it carries 200 or more channels. The user then is going to choose a single channel and the rest are going to be filtered out. In opposition to this, we have baseband, where you're going to use all of the frequency of the cable all of the time. So a telephone, for instance, uses baseband communication, which means that when you pick up the phone, you're using all the bandwidth allocated to that phone line. This doesn't hold true with the cable TV signal, right? Because we had 200 channels all using some of that bandwidth, but we only pulled out the ones we wanted. For this reason, we can only make one call at a time when using a phone, but we can have 200 channels or more on our TV. Now, when we use baseband, we're going to use a reference clock that allows us to send the information for both the sender and the receiver at the certain time. By using this reference clock, this is an example of using asynchronous communication. Another good example of a baseband network is a wired home Ethernet network, because this is going to use all of the frequency that's available on your cable, giving you more bandwidth than you would if you had a broadband area. Now, in this case, if we have a single baseband using up all of the bandwidth, we need to figure out how to get more out of it. And so to do this, we have a couple of different mechanisms we can do. And the first one of these is what's known as time division multiplexing. In this mode, each session is going to take turns using a dedicated time slot to get part of that bandwidth from the baseband. Now, an easy analogy to this is if you have a house with a single TV in it, but you have 4 family members. Everyone wants to watch TV, but there's only one TV, so they're going to have to take turns picking what program's going to be on. Now, in a pure time division multiplexing environment, each person is going to be assigned a time slot, and they can pick whatever TV show they want during that time slot. Now, this may or may not line up with the time that their show is actually on, and that could cause a problem, right? So we have this second method called statistical time division multiplexing, or STAT-TDM. This is a more efficient version of time division multiplexing because it's going to dynamically allocate these time slots based on when people need it. So if we take our TV example, maybe, for example, I want to go down and nobody's watching TV at 8 o'clock, but it wasn't my time slot. Well, under time division multiplexing, I couldn't turn on the TV because it wasn't my time slot. But with STAT-TDM, I can, because as long as nobody's using the TV, anyone's free to use it. Everyone's going to take turns based on their necessity, not based on the time itself. So instead, when I start watching the TV at 8 o'clock, then after my 30 minutes is up, I'm going to get off at 8:30 so somebody else can get on. Even though my assigned time slot under TDM might have been something like 9 to 9:30. Now, our last method is what's known as frequency division multiplexing, or FDM. This is going to involve taking the medium, that cable, and splitting it up into channels similar to the way we do in broadband. So if I take a single cable and I break it up into 50, 100, or 200 different frequencies, then each person can get a small portion of frequency allotted to them and they can use it as much as they want. Now, for the exam, the good news is you don't need to memorize TDM, STAT-TDM, and FDM. But rather, you just need to understand that multiplexing involves taking some limited amount of resource and using it more efficiently. In the real world, you may come across these multiplexing techniques, especially if you start working as a network engineer or a network architect. And that's why I wanted to introduce them to you. But for the Network Plus exam, just remember, multiplexing allows multiple people to use a baseband connection at the same time. The final thing we need to talk about in this lesson is some examples of physical or layer 1 devices. The most common one is going to be a cable. So if I have a fiber optic cable or an Ethernet cable or a coaxial cable, these are all different types of media. And if I have different types of media, that's considered a layer 1 device. The reason is whatever goes in one end of the cable is going to come out the other end of the cable. So if I have a fiber optic cable and I put light in one end, I'm going to get light out the other end. That's a physical response, a physical layer of the OSI model. Additionally, beyond wired cables, we also have wireless things like Bluetooth and Wi-Fi and near-field communication. All of these radio frequencies make up the media at layer 1 for those type of networks. The final example is infrastructure devices, and that would be things like hubs, access points, and media converters. All of these devices operate at the bit layer. This is going to be a function to just simply repeat what they get. So if I have a hub, whatever goes in port 1 of the hub is coming out ports 2, 3, and 4. Whatever comes in gets repeated out. The same thing with a media converter. If I have something coming in over coaxial, it's going to get converted through media and pushed out over fiber optic. That device is simply doing it at the physical layer. Whatever comes in is going to go out. There's no logic to it. There's no intelligence to it. Layer 1 devices simply repeat whatever they're told. Now, we'll talk about some other infrastructure devices as we get into layers 2 and 3 and 4. But for right now, I want you to remember layer 1 is dumb devices. They're simply repeaters. Whatever they take in, they send right back out.